Bonjour.
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 Bon, donc je comprends qu'on attend les autres membres du jury.
Oui, vous êtes
Très bien,
deux pour le moment être présents,
très bien.
les membres français.
Pour une fois que les Français sont à l'heure.
Euh, Ils entendent ici. Ouais. Là, ensuite, toi, tu peux te connecter à la visio aussi. Je sais. Il y a un revue aussi non. Pour l'instant, il y a Formidable et Michel Sébastien. Hi Florent, hi Michel.
Hello Bertrand.
Um, Michel, would you like to act as the president for this defense? On peut parler français d'ailleurs. Michel?
J'ai entendu parler il y a 2 minutes.
Son micro fonctionnait il y a quelques minutes. Et là, il est Michel, tu es muté? Excuse-moi, je vois pas.
Yes. Oh, sorry. I said yes. It's all right. This is not a complete surprise for me.
Yes. If you got my mail yesterday evening, yes.
Yes.
So you have the document for the defense, or because we have to sign the document. So do you rely on me to fill in the document and to pass it to you, or how do we do?
Um, what I would prefer is this. That is, you take in charge all the documents because this will be. I think that anyway, the PhD advisor is supposed to fill the documents and then to transmit this to the doctoral school. So what we'll do is to write the report together at some point.
Yes.
On say an overleaf or something during the deliberation. And then
okay, I copy paste it, and then you have to sign the document, all the committee.
And then oh yes, and then you can send me the PDF, and then I can sign it, and I can sign for all the members, or except you, of course.
Okay, great. Let's do that.
Good.
Do we have no, thanks for joining. And Jonathan and Christophe, can you quickly check that your microphone is working correctly with Zoom?
Hello, you hear me?
Hello, yes.
Yes.
We can hear you.
Okay, and the camera now is working. Don't
Perfect.
ask me.
We can come together.
Hello, Christophe.
Hello, hello.
And you're still
Waiting for a last member of the jury. I think it's quite early. In my last email, actually, I sent both the Zoom details as well as the right YouTube link, but they should definitely connect on the Zoom. Hello, Sami. Thanks for joining. Can you hear me?
Morning. Yes, I can. Hi, everyone.
So thanks a lot for joining. I think we can hear everyone here. And we have our jury that is complete. So yes, I let the president of the jury say a few words if she wants. Michel, do you want to say a few words to introduce the committee?
Yes, but do you think that the jury is completed now?
Yes, the last member just arrived.
Okay, so hello everyone. My name is Michel Sebag, and I'm here to act as president of the jury of Thomas Bazeille PhD Defense, and we are here to hear this defense about his work. So Thomas, you have 45 minutes, and welcome everybody.
Thank you very much. So I'll just get my setup ready. All right. So welcome everyone, and thank you to join this defense. Thanks a lot to the members of the jury for accepting to review this work. And thanks to all the people attending. So today I'll present to you my thesis work. And this presentation is entitled Template Estimation for Arbitrary Alignments and Application to Brain Imaging. So first I'd like to give a little bit of context about functional brain imaging methods and concepts. The main tool that we will use here as of data acquisition is functional magnetic resonance imaging, or fMRI. Basically, fMRI acquisition sessions take place in a few 15-minute sessions in which each subject is presented with an experimental protocol which is carefully crafted. During this protocol, we show some stimulus to the subject, and these stimuli are designed to produce some specific mental states. Meanwhile, the acquisition scanner records a signal which is called the blood oxygen dependent signal and is correlated with neural activity. In this way, we're able to have functional imaging data which record activity in the brain while the subject performs this protocol. These data are 3D images composed of volumic pixels or voxels, and we have roughly one image every 2 seconds and several tens or even hundreds of thousands of voxels per image. Using those images, we can perform several tasks in cognitive research, and one important task is functional brain mapping. A first kind of brain mapping can have the goal to infer which brain activations are caused by a specific experimental condition. So to do this, usually we look at the voxel individually, and for each voxel, we try to relate its activation with the set of stimuli that were presented to it, and to find relevant, significant statistical link between activity and those stimuli. We do this through general linear models, and the regressors, the beta we managed to extract from these models, then can be processed to have some functional contrasts. So for example, here I plotted a contrast of face image processing versus other images processing, and we can see specific brain activation to face image processing. Here it's a relevant brain region, which is called the face fusiform area, and is responsible for face image processing. When we use several different contrasts all together to characterize some regions, we can have an extensive view of for each region in which set of different condition it is involved or not involved. And so we can find some homogeneous functional regions that will be that will respond in the same way to experimental conditions. Or for example, here Glasser et al., from whose paper this figure is extracted, also used this characterization to perform a parcellation of the brain into small functional regions. A final type of brain mapping that can be done can be to try to identify which experimental condition a subject was seeing directly from activation patterns that we observe. This is usually performed on flattened brain images. And here we search for patterns of voxel activations that will be very specific of one particular stimuli. We fit a machine learning model on those images and tune this parameter to have the best prediction possible. And then we can test how well it predicts stimuli for new data and measure the accuracy of such a model. We can also inspect the weights, so the features of this model that will be that will enable a good prediction, and see which voxels hold discriminative signal across stimuli. So in this presentation, I want to talk about an important limitation of functional brain imaging, namely functional variability, and about methods that are designed to handle it, such that are called functional alignment methods. Then I'll introduce some methodological developments we proposed for this family of methods, as well as a benchmarking that we performed using inter-subject decoding to assess the gains from functional alignment. So first, it must be noted that variability is a core characteristic of brains and subsequently of brain images. If we look at brain pattern of brain images from different subjects, so here each row is a different subject, we can see that their anatomy varies widely in the shape and size of different brain structures. And so obviously it's hard to compare images of different subjects. To address this problem, we perform anatomical registration to bring all information in a common anatomical space. So after registration, all those images seem to look alike. However, the functional activation patterns that we observe are still varying quite a lot. If we focus on the body minus average contrast, which is a contrast of people seeing images of body minus seeing other type of images, we can see that activation patterns of each subject are different in terms of locations, of peak intensity, and in overall shape as well. So it's hard to deduce from those images which brain region is really involved in body image processing. In some other contrast, we can see even more striking differences, such as large activations throughout the brain for some subjects and no activation at all for other subjects. Overall, functional variability is also a core characteristic of functional brain images, and it can be explained through different factors. First, there are some very stable factors, such as genetic or brain structure factors that will influence brain activations and their locations. Plasticity also, and the way the brain evolves through life will create some differences across subjects. On a less stable time scale, different cognitive strategies can also be used by different subjects to perform the same task and thus depict different activations. And finally, some very daily factors such as the mood state or the task familiarity of a subject will influence quite a lot the activations we then observe. And this functional variability overall has very serious consequences for cognitive research. First, it prevents researchers from attaining high-resolution functional brain mapping. And in some very highly variable regions, it can also even prevent us from understanding exactly in which functional processes a region is involved. On top of that, it also prevents us from doing population models of the brain and to learn some generalizable conclusions about brain organization. And in some specific case, it can also cause an entanglement of functional networks that are close by and that we can confound, that are confounded by variability. To overcome these limitations, several studies changed quite a lot the acquisition paradigms. So traditional large-scale studies used to acquire a little data for many subjects, hoping to have generalizable conclusions about very specific functional networks. And newer large-scale acquisition initiatives often focus on acquiring less subjects, but with a very high number of acquisition sessions per subject in order to have a very precise characterization of individuals. But then the question remains, how do we match those characterizations together? So a family of methods was designed to address exactly this problem, and it's called functional alignment. It stems from the idea that if we know how a voxel activates throughout a large set of contrasts, we have a characterization of it. So here, for example, if we know how a few voxels activate for 4 contrasts, we can deduce its activation profile, so its activation value in all those contrasts. And those profiles can actually be seen as coordinates in a high dimensional space, which we'll call functional space. In this space, obviously, the spatial location of voxels have no importance at all. And the variability that we observe creates a dissimilarity in this space, meaning that the same voxels for different subjects will not be located at the same place in the functional space. The idea of functional alignment is to take a small region of a few hundred voxels, for example, and to try to match each voxels of one subject to the voxels of another subject solely based on their functional characterizations. So in terms of the underlying mathematics, it's the idea of matching clouds of points in this high dimensional space. The first method that was proposed to do so is called hyperalignment and was introduced by Axby et al. In their Neuron 2011 paper. Basically, it proposed to search for functional matching as an orthogonal matrix. And so to solve equation 2, where we search for R, which is orthogonal, and an additional scale factor sigma, which enable us to match the norm of aligned data with the target data. This can be easily solved through a singular value decomposition. So overall, it's a cheap method to find matching between voxels. However, it must be noted that it's both local, meaning that we can only apply it on small portions of the brain, and pairwise. So it only applies between pairs of subject and images. Another method which was introduced later by Chen et al. In 2015 is called the shared response model. Here we have data that is still in correspondence, for example, time synchronized across subjects, and we want to find a matching. Here we find this matching as a common spatial decomposition. So each subject's data is decomposed into both an individual set of spatial components, which can be seen as modes of activations of the brain, and common shared response, which are time courses for each of these spatial components. This can be formalized as a joint minimization of this decomposition for each subject, which must reconstruct well its original data, and with the constraint that spatial components are orthogonal matrices. Overall, it can be solved through alternate minimization with a lot of computational efficiency. and provides here a common decomposition of several subjects. However, it's still a local method. Plenty of other methods were proposed in the literature to perform functional alignments. Some of them are linear and mostly rely on the same ideas that we already evoked. A few other are non-linear, but usually don't really translate to the typical cognitive research use cases. An interesting family of method, which was also developed, is based on the idea of finding diffeomorphic transforms between two subjects, so continuously, especially continuous transforms that will be guided by functional similarity. However, those methods are often very constrained by this spatial continuity that we impose and are not always able to really handle the variability, which is a strong factor. What must be seen across all those methods is that there remain several challenges in this field. First, there are still some methodological shortcomings. For example, most proposed alignment methods are local, and we miss a way to aggregate many local alignments together to perform full brain alignments of subjects. They're usually which means that it's easy to align two subjects together, but to align large cohorts of subjects, we still miss a good heuristics to find the template space to which all subjects should be aligned. And finally, the current implementations of methods that were proposed don't really scale. On top of that, the benefits of these methods for cognitive research are loosely known, and the use cases are ill-defined overall, meaning that it's hard for a cognitive researcher to understand which alignment method to choose and how it will perform. So our work in this PhD was mostly motivated by those shortcomings that we tried to address. And so first I'll introduce some methodological developments targeted at the problems we already mentioned. Optimal transport alignment can be first seen as through the eyes of a very old problem, which was introduced in the 40s. And basically, this problem called mine and factories can be described like this. We have 4 mines, each of them producing a different quantity of resource, A1 to A4, and 3 factories producing different, needing to consume different quantity of resources, B1 to B3. Now, the cost to transport a unit of resource from a mine to a factory is different depending on the distance between the mine and the factory. So knowing that we need to transport all this resource and all of those costs, what is the best matching we can find to the optimal transport plan that will efficiently transport these resources? More formally, this can be described through this equation, where we search to find the coupling or the optimal transport plan R that when multiplied element-wise with the cost matrix C will yield the overall lowest possible cost. This minimization is done under constraints, since we must respect what are called the marginal constraints, meaning that all quantity produced by a mine must be displaced and each factory must receive exactly the quantity it needs. How is this related to alignment? Let's go back to the problem of matching 2 clouds of points in the functional space. And actually, here, if we define the functional dissimilarity as a cost matrix, so meaning that for 2 voxels, their functional difference, the difference between their activation profiles, so their dissimilarity is taken as the cost to displace them. Now, finding the optimal transport plan is actually the way to minimize the overall dissimilarity between subjects. And so we can actually apply exactly what's called balanced optimal transport to perform alignment, as was presented previously. Actually, we introduce an additional regularization using the entropy of the coupling, HR, and we add it as a regularization in equation 5, yielding equation 6. So this entropy helps us solving more efficiently this problem and yield more stable couplings, as was explained by Couturier et al. in their NIPS 2013 paper. So how does optimal transport compare, for example, with Procrustes on a toy problem? Here, I plotted two distributions, one source distribution in green and one target in red. Those distributions can be seen as voxels characterized by two features in the functional space. Now, the original anatomical alignment that I imposed between those distributions is faulty because voxels have undergone a translation. If we try to find a better matching using Procrustes, the alignment we get actually kind of recovers the translation that was applied, as can be seen in the orthogonal mixing matrix. However, it also underwent a very strong smoothing, and many source samples are used to predict the data of each target sample. By comparison, if we apply optimal transport here to find the alignment we search for, we get through this overall minimal cost constraint, a matching which is way more sparse between those voxels. And we also recover more exactly the translation that was applied. Now, this method, optimal transport alignment, as overall we presented, is local. And so we need schemes or way to perform this analysis at a whole brain scale while still learning local methods. If we just try to apply, for example, optimal transport on whole brain images, it might yield non-local correspondences. For example, matching contralateral areas together because they are kind of similar signals. However, this matching is definitely not needed. Moreover, most methods won't scale to full brain resolution. So instead, what we propose is to first start with a parcellation that can be derived either through clustering or through a functional atlas that is previously known. And on each parcel, find local alignments. And then we can use all those local alignments to recompose a whole brain matrix as a block diagonal matrix, which still holds the exact regularity which was searched for locally. For example, if we search for an orthogonal local matching using Procrustes, the whole brain alignment will still be orthogonal. By contrast, another method which was proposed in the literature and is called searchlight do not really enforce the same regularity at the whole brain scale. This is because instead of working on a set of non-overlapping parcels, it worked on overlapping balls with a fixed radius, each of them centered on a given voxel. And so at the overlaps of different regions, the alignment that are sought for are actually averaged, losing the overall regularity. So piecewise enforce this regularity. However, it can still induce some border effects. We introduced another computational scheme or heuristic to be able to match several subjects to a common space. Because the question now is which common space should we choose to represent several different subjects? The first one we could think of would be the Euclidean mean of subjects. However, this mean destroys the signal structure, and so it doesn't preserve the information we need to perform right alignments. So instead, what we proposed is to gently learn the template T when we learn the alignments, solving equation 7. This can be solved using alternate minimization. So in initialization, we first fixed a template, for example, as the Euclidean mean. Then we learn alignments of each subject to this template. And when we have learned these alignments, we fix them and infer the best possible templates from these alignments, for example, solving least square in the T step. We can iterate this process several times, and each time we will improve our template and yield more precise common space to which we could align. How can we assess all those methods we introduced? So a common way to assess alignments is to see them as reconstruction techniques, since they try from one subject to reconstruct the data of another subject. So here, what we can do for assessing templates methods is first to infer a template from a set of subjects, and for several different contrasts, take a left out subject and learn alignment from this subject to the template. And then only using part of the data that we have available in the template. And then we can predict through the alignment and the data that remains, some new data for the target subject that we can compare to the ground truth. This scheme is what is usually done in the functional alignment literature. And here we perform that using the individual brain charting dataset with 12 subjects. And for each subject, we have 106 contrasts, which we split it in half between a train and test set. Now we can see how well we predict new data for the left out subject. And if we look at voxel-wise metrics, so here, the R-eta square metric that we used says for each voxel, whether it was better predicted with alignment than it was without any alignment. So here overall, most voxels are better predicted through various functional alignment methods than they were without any alignment. However, this hides the fact that qualitatively, all those methods behave quite differently. Here we looked at another matrix, which is the raw prediction score, just normalized. And for each voxel, we can plot this prediction accuracy. And if the value is above 0, we predict, it means the prediction is better than predicting no signal at all. And if it's less than 0, it's worse than predicting no signal. Here, identity in the top left corner denotes performing no alignment at all. And what we can see is just taking the average of subjects data that we had in the first place is already a very good predictor of activation of subjects we don't know in the same task. Because in the visual and auditory cortex, the signals seem quite stable across subjects and alignment doesn't seem completely needed. However, in other regions, it performs very badly and some functional alignment methods seem to perform better. For example, scaled orthogonal makes less errors. However, it does so through predicting no signal at all, which is obviously not yielding any interesting facts on those left out subjects that we can reuse in other tasks. By contrast, optimal transport make a few larger mistakes, but predicts also way better a signal in regions that were previously not aligned well. So this is a sign of a good alignment. So for now, we've introduced optimal transport as an alignment method. We also introduced a piecewise analysis scheme to perform this alignment full brain. And we also released some scalable implementations of that, openly available on GitHub. However, we also observed that the methodological validation of those alignments is quite tough. In fact, the metrics that we used are biased and they are very sensitive to low-level images, images characteristics. For example, alignments yielding very smooth images were actually performing well when assessed by those metrics, but not yielding any meaningful information. On top of that, the template that we saw for now, we can't really measure how well how good a representation of the data it is, since we don't have any ground truth to which we could compare it. Even worse than that, actually it suffers from a strong indeterminacy, meaning that in this equation we minimized, actually we could at any time multiply the template by an orthogonal matrix and each alignment by its transpose, and we would recover exactly the same minimization result with a widely different template, meaning that the template spatial locations that we observe are not stable at all and could be changed while remaining optimal in this sense. So this template, for now, we can only see it as a computational intermediary step, but not as a real data representation that is stable. So building on those limitations that of the metrics we used until now, we decided to proceed in another way to benchmark alignment in real world use cases. The idea here is, instead of trying to assess the alignments themselves, try to assess the information that they manage to recover. And to assess this information, we want to measure it through a downstream classification task that uses it. So here we start from a set of labeled images, for example, contrast or trial images. And usually inter-subject decoding means just taking those maps for several subjects, training a machine learning model to decode those maps and to predict their labels, and then testing it on a left-out subject. This process is actually subject to variability, and its accuracy is decreased because of variability. So instead, we can add an additional step in our analysis pipeline, so alignment. And here we can align using completely independent data, each subject to the left-out subject. Then those alignments can be used to transport or to align all data, decoding data that we will use in the same space. And the decoder can be trained directly in this space. So the decoder trained here should be less sensitive to variability and better suited to predict new data from subject S. Here, this difference in decoding accuracy will be our metric. So we used this improvement as a metric, and to have it not interact too much with the decoding model we chose, we fixed a simple decoding model that doesn't require really fine-tuning. So we chose a linear support vector machine. We also chose to work both at the whole brain and region of interest scale, so local scale, since we saw that this resolution is important for alignment. And finally, we focused on pairwise alignment methods, since, as I told you, the template is actually just an additional heuristic for computations, but cannot really be seen as a different method. With this benchmark, we investigated several questions. First, how do Piecewise and Searchlight compare in terms of aggregating many alignments together? Then, which alignment method perform best among optimal transport, Procrustes, and the shared response model? And finally, how do those models impact the data on which we apply them and the activity patterns that are resulting? Do they still preserve some specificity of this signal that we can reuse in other tasks? For this data, we used for this benchmark, we used 4 different data sets. 4 of them comprise between 4 and 10 subjects. They have different alignment data type. So for some data set, we used contrast maps as alignment data. And for some others, we used raw maps, just pre-processed, for example, of audio movie listening or movie watching. The type of content that is decoded varies also quite a lot across data sets. In IBC, it can be language or auditory decoding tasks. And in some others, it can be visual. For example, in BOLD 5000 or Courtois Neuromod, those are visual decoding tasks, so targeting different functional systems. So now I'll present the findings of this benchmark. And so first, to understand this graphic, we say that this each point here is a different subject accuracy, decoding accuracy. So for one left-out subject, how well we managed to decode its data. And here the 0 is the decoding accuracy without any alignment across subjects. And so for each point is the improvement compared to no alignment for a different alignment method. What we can see is that overall, there are several methods that perform well to improve decoding accuracy. For example, Piecewise shared response model or Piecewise optimal transport managed to improve accuracy by roughly 5%. On another note, we can also see that Piecewise is more efficient than Searchlight. Here it performs way better to improve Procrustes efficiency. To give a little bit more context about what these gains really mean, we can compare it with decoding directly in one subject space. So within subject decoding, here means training the decoder directly on the subject's data and testing on the same subject's data. So the variability here has no impact at all. And when we do that, we see that our decoder perform on average 8.5% better. So here the 5% gains of the best functional alignment methods actually recover more than half of that, which is quite impressive because it means we can target as much as half of the impact of the variability and remove it just through statistical processing. To be complete, we also assessed the efficiency of different algorithms. And the main things we can see here is that shared response model and piecewise Procustis roughly perform in the same computational time, while optimal transport is way slower, as much as 10 times. And Searchlight is also way slower compared to piecewise, 25 or 13 times on average. We replicated the same experiment at the local, at the region of interest scale to compare methods without any aggregation scheme. So here we worked on region of interest that are depicted on the right, and we learned alignment on the whole region at once. So those are large alignments, and performed decoding exactly in the same regions as well. What we can see is that the accuracy gains are mostly preserved. The best methods still recover roughly 5% accuracy gains, even if the baseline changes quite a lot. Here, shared response model performs a little bit less well compared to optimal transport, mostly because of its performance on the neuromod dataset, and Procustis is very weak as well. In terms of computational time, it's very similar to what we've seen previously. Optimal transport is still 10 times slower than Procustis, and shared response is very efficient. A few more findings of this benchmark. First, when we use the piecewise alignment scheme, it relies on a parcellation that we choose in the first place. And here we compared several types of parcellation, either from functional atlas or through clustering algorithms. And in fact, it really doesn't matter so much which type of clustering we use and what is the resolution that we take for this clustering. Alignment also is often compared with smoothing, meaning that many people asked if applying an alignment method just doesn't have only a smoothing effect that is non-isotropic. And so to compare those, here we performed Gaussian kernel smoothing on top of our original data and see whether it enabled us to improve our decoding accuracy. In fact, it doesn't reach the same kind of gains as Procustis does, since most smoothing kernels actually decrease decoding accuracy. Finally, we also compared the impact of the representation of data we use, because it's often been argued that surfacic representations of data are better suited for alignment than volumic representations. So here, what we did is we took the same data in both 3 millimeter volumic representation and high resolution surfacic representation on FH average 7, which means roughly 150,000 vertices. And we see that overall, the type of representation we choose don't change drastically the gains we can observe, even if surfacic here and the high resolution as well seem to help a little alignment to perform well. Last experiment we did to compare the geometrical effects of all those methods is to focus on specific contrasts and see how they are impacted by alignments. So here what I show is some contrast for a left out subject, the 4th subject of individual brain charting dataset. And we see that those contrasts are quite precise. Now, if we compare them with some contrast for other subjects, some group effects after alignment, here anatomical actually depicts no alignment, so group effects without any alignment. And we can see that those contrasts are really smoother. When we apply functional alignment, we manage to recover some sharpness of those contrasts and some locations that better look alike the ones of the target individual. What it means is that those methods that perform well manage to recover meaningful topographies, and so this signal can be used then for other tasks or for activation identification without any specificity loss. On the contrary, some other methods, such as piecewise Procustis, are a bit weaker in terms of the group effects they manage to recover. we did this on a couple more contrasts here in the language cortex instead. And here we can still see that the anatomical alignment alone, so without any functional alignment, don't manage to recover precise group effects, whereas after alignment, those patterns are really sharper. So overall, what we've introduced in this thesis are novel optimal transport alignment methods, which yields very good results. A piecewise alignment scheme, which is also can be applied to existing models, such as the shared response model, and some scalable implementations of that. And we additionally shown that those methods are actually useful in practice for researchers because the decoding, as we did, is a common task that we find in the literature. So best methods of alignment can recover much of the accuracy that is usually lost because of variability. And we've given several methodological guidelines on how alignment should be applied. We've, for example, shown that piecewise is really a better aggregation scheme than Searchlight. The perspectives for this work. So short-term perspectives are extensions of this study, such as the study of how does the learning data impact the quality of alignment that we learn, and also to investigate how the resolution of the images we use impacts the quality of those alignments. And in the longer run, very interesting perspectives would be to use instead data from different data sets and be able to bridge subjects from those different data sets. Usually, this means that we don't have any correspondence between features as we have in classical alignment methods, which needs novel methodological developments. And finally, an important question is to find ways to overcome the functional template indeterminacy to be able to perform inference in the common space after alignment. With that, I want to thank you all for your attention and to thank also the people with whom we made all this work. So Bertrand Thirion, my advisor, as well as Elisabeth Dupré, Hicham Janati, Jean-Baptiste Pauline, and Hugo Richard, with whom we worked extensively. Thanks a lot.
Thank you, Thomas. It was a pleasure to hear you. So as the usage wants, I will give the floor to Professor Oluwasanmi Kojezo from the University of Illinois at Urbana-Champaign, who reviewed your work. Professor Kojezo, you have the floor.
Thank you. This is the first one of these I've done, so it's at least in Europe, so it's possible. I just want to make sure, I guess, let me know if I'm following how the European system works as I go along. I'll depend on the rest of you to tell me. So Thomas, I think you did a great job both on the thesis, which I read, and also on the presentation today. I think the area broadly of optimal transport is an important one that hasn't been explored as much in neuroimaging and neuroscience broadly. And I appreciate you taking the plunge and considering this area of work. And I think you found some quite interesting results that are suggesting a very promising direction for thinking about these kinds of tools. There's also a lot of other research in optimal transport, and I think I'm optimistic that many of the recent advances and methodologically will also make their way to improving some of how we build neuroscience imaging analysis tools. I also like they use open source data, and you have open source code, which is great, so others can build on your work. I think in my reading, my biggest concern, which you ended up addressing, was evaluation. I think the sort of reconstruction, as you pointed out, clearly has holes and biases, and you suggested using instead prediction, which seemed like a better tool for trying to get a sense of how the method is working. I could ask a question. I don't know if these are just summaries or if I should also ask a question. I'm curious, what's the should I ask? Am I open to ask questions now or not?
Yeah,
Okay.
I would also appreciate some instructions. What would you?
Yes, indeed. So okay, so this is exactly the way you proceed. You emit some general comments about the PhD, and then perhaps also the manuscript, and then you ask questions about all points that you wanted to clarify.
Okay. I don't, thank you, Michelle. I don't have questions on, or I guess deep questions on the content. I think both the writing itself and this presentation here seem pretty clear to me, but I have maybe future facing questions that I'm curious your thoughts on. So these are maybe free form, less precise. So I think part of the benefit that you're pointing to, particularly in predictive settings, is the ability to better deal with location equivariance or invariance depending on the setting. So the fact that activity might be in different locations. Do you have a sense of how this might compare to, say, deep learning methods, which particularly, say, convolutional methods, have potentially the property of being able to be less location specific, if you like, in terms of the signal, how explicit alignment might compare to sort of more direct predictive approaches?
So this is a very interesting question. I think overall it hasn't been tried so much in this field. Some deep models. I remember only of one paper that has done something comparable. And it's very data specific, because the main hurdle here is the amount of data that we have in fMRI, and given the resolution and the size of the images, being able to train specifically tailored networks is still a big challenge, and I think it won't change so much in the forthcoming years. So, but overall, this can be clearly seen as in general image processing. This is clearly an interesting way forward to target inter-dataset variance, and I think many transfer learning algorithms rely on convolutions. Yeah, but
yeah, that makes sense to me.
Yeah.
Maybe one other future-facing generic. I'm going first, so I get to ask all the questions. I'm curious also, I know that there is early work thinking about alignment in the context of functional connectivity. I'm curious the extent you think the specific approach using optimal transport might change. Do you think it's just plug and play in the methods they're considering functional connectivity, or do you think there are fundamental things that might need to be tweaked to get it to work for connectivity approaches?
So there are different kinds of methods relying on functional connectivity. One popular line of work is the one from Axby, introduced by Guntupalli and al. In 2018, I think, basically trying to reconstruct some synchrony between features when we only have some resting state data that are non-synchronized by design. And so what they're doing is just reconstructing some features that are common across subjects using connectivity IDs. And here, so we have, if we have synchronized set of features across subjects, for example, it's completely plug and play, because optimal transport here is just a way to match those set of features together. However, there are other techniques that learn connectivity that use connectivity to learn more complex things, such as embeddings. But here still they use usually processes after those embeddings to match distribution together. And so optimal transports can really be seen as just another way to do matching, shape matching, instead of using processes. So it would still be plug and play. So I think this is a very interesting direction, by the way, connectivity alignment, because of the challenge of matching subject data sets that have no common data or really synchronized data. It's really a tough one. And so this is an interesting way to do. However, we still saw in some comparison that it's not as powerful as when you have synchronized data, which makes sense.
Great. Thank you. I don't have any other questions.
You don't have, okay. So perhaps if at some point in the during the defense, some other question comes to you, then feel free. You'll have the floor again. So now I will give the floor to Professor Christophe Philips from the University of Liège, who also is reviewer on Thomas' PhD.
Hello, Michel, Thomas, Bertrand, and all the other jury members. Thank you for inviting me to be on the jury. And yeah, how long do we have actually all together? It's that I don't want to spend a whole day questioning, and I'm sure Thomas will agree with me on that. But is there some time frame we should be respecting?
Well, we are rather free, right? Depending on the European country, I remember that in Finland you were supposed to ask questions for hours, but let's say that here, where we will be happy if you ask, say, some 2-3 questions. That's perfect. But anyway, if you have burning questions, no limit.
Yeah. Okay. Yeah. Thanks. Well, first, some praises. So I did read the thesis from the first to the last page, and it was a very instructive document. And I must say that I was not really on top of things in terms of functional alignments and these approaches, and therefore I must thank Thomas for teaching me some things, and I think that's a cool thing on being on a jury, is also to be able to learn from the students, and also he addressed a few of the comments I made, and so I'm all happy with that. And his presentation today was also very clear and didactic. I'll start with very general question, and a bit like my colleague, I will not get into too many technical details. It's more perspectives and global questions. So as the starter, in your opinion, you show that it does make quite a difference to do this functional alignment, but that's clearly not that common. So what is for you the major hurdle at the moment for these techniques to be just not so used? Is it a question of because they're not understood or by the neuroscientists, or time to acquire specific data, or easy to use tools? What is the
Thanks a lot. So this is an interesting question. Actually, when we started this PhD, we weren't really thinking that functional alignment would help a lot for predictive tasks in practice. So yeah, no one was really optimistic about that. So I think it's a common thought. It's because those methods are mostly not well known, and they are really assessed in ways in the literature that don't make a reader sure that they would generalize in some common use cases. So we lack, I think we really lacked some benchmarks, and that's also why we really spent some time performing all those experiments to show on several different setups whether it would help or not. So I think, yeah, first it's a lack of information and clear results. That's what we try to provide partly. On top of that, obviously you have to have some alignment data, if possible, at least for evaluation completely unrelated with other data. So it's already restricts heavily the data set that you can use alignment on. However, still you could apply, philosophically, there would be no problem to apply alignment using the same, your data, if it's task-based, for example, directly before performing other inference process. But yeah, people often think that it's needed to have separate alignment data. And here we restrict it to that as well. So obviously it makes, restricts a lot the scope of use cases in which it's useful.
Yeah, it makes sense. So also from your example, it seems that the data that you're using are mainly coming from quite simple or basic contrasts, like visual stimulation, visual discrimination, and so on. How well does it generalize to I would say, I don't know, like auditory stimulations, and more importantly to more complex brain activities like memory types, executive functions, and stuff like that. Would that work well or
yeah,
not?
that's a very tough question. Basically, there are two questions in that. First, how much would the alignment we learn make sense, and how good that would be in different parts of the brain, and also are we able to assess correctly alignments in all parts of the brain? And so that's a limitation of this decoding study, is that every decoding task has some special ascription to the voxels it really probes and uses. So actually, we made additional studies on that. It's part of work to come. And what we saw is that for decoding tasks, don't probe all the cortex. However, they still probe a significant part of it. So when we have several different decoding tasks for the same data set, which for example, the individual brain charting data set is really very valuable for that. We're able to assess alignments across a significant part of the cortex using different tasks, but still it's not the whole cortex. Then if we speak about how well it works in some areas that are non-sensory and non-motors, in fact, it's really difficult to test, because we didn't find, we were actually trying to make this point to know exactly that, and we didn't find so many decoding tasks that worked and had conditions not priming basic sensory networks. So actually, we lacked a bit the data to answer this question, which is obviously of interest. But the hope of functional alignment is that even if it was proved in sensory regions, because it's also where it's easiest to show, it would help those characterizations that we find are stable enough in other parts of the brain. But I agree that for now, it's not completely.
Yeah, I mean, yeah, it also depends on the data you have at hand, and yeah, but yeah, it would be interesting to push in that direction. I had also some idea crossing my mind when listening to you today. So I don't know if it's a good idea or a bad idea. So you'll tell me. In with MRI, we use the deformation information to do, well, there is sort of morphometric analysis across groups of subjects and so on. So in a way here, you are not aligning the anatomical structure, but the functioning of the brain. So I was wondering, and that's my silly or not question, if these spatial deformation could be used to characterize your subjects as much as we do it for anatomical alignment. So would there be some information to gain from this functional alignment as much as we do with anatomical alignment?
So yeah, the alignment transform itself, you mean?
Yeah. So I play a bit with the anatomical images, and you know that if you see a place that needs to be enlarged to match the other subjects, that's because it's already there was some gray matter thinning over there, so some kind of atrophy. So you've got the information about the atrophy or not based on how much deformation you need to apply. So here, instead of anatomical atrophy, what about functional atrophy? Would it make sense? Oh, first, is it possible to derive these kind of things, and how would we be able to use that? And
so I think so it's still a quite different context, but so simple ideas could be used, such as, for example, we never actually did it, but we thought at some point about measuring at least the norm of or the local norm of alignment to see how much variations are needed to match signals in a specific area across subjects. And so, for example, you would have some effects that you would expect, but subjects showing different or being from different cohorts would need more alignment than subjects from the same cohort if they have some characteristics in common. So I think this can be explored for sure. Then the main question I have is that those alignments are quite different from the diffeomorphic alignments that are used usually for anatomical registration. And actually the regularity of an alignment makes it easier to interpret it because it's part of a smaller family of transform. And it's also better characterized when it's more strongly constrained. So we understand well what a continuous transformation should do. For alignments that are really not constrained, such as Procrustes operating in very high dimensional setups, it's tough to understand what really would mean to have a high norm alignment, for example, locally, and to derive more subtle characteristics. For optimal transport, which is a bit more constrained and well-defined, probably we could try to derive something in that.
Good. That's just ideas that crossed my mind. And yeah, for the moment, I'm quite happy with the questions. If I think of something else or I jump on following up with someone else's question, I'll let you know.
Yes, of course. So thank you, Christophe. So now I'll give the floor to Professor Jonathan Pillow from the Princeton Neuroscience Institute. Can you hear
Sorry
me?
about that. Yes, thank you so much for inviting me to be on the committee. And Thomas, I want to congratulate you on a very excellent thesis. And I think it attacks a very important problem that has been very understudied. I'm a little bit familiar with alignment methods because my colleagues at Princeton were the ones who developed the shared response model. And so I followed a little bit from the outside, kind of the progress that they've made in attacking this problem, but I wasn't aware of many of the other algorithms that you covered or of sort of some of the technical problems that are associated with benchmarking these different methods, comparing them to each other. So I think your work is both very creative and novel solution to the problem, and it also does a very nice job of unifying these different methods and providing a platform. I think that's something we need in the field much more. Something machine learning has benefited from a lot is the use of benchmarks to allow people to compare methods easily across standardized set of metrics. And so I think that'll be a major win for the field, even as other methods come along that are maybe better than what we have right now. So anyway, I'm delighted to see that. So congratulations on a very nice thesis. I did have some technical questions, if you don't mind. A lot of this is my own unfamiliarity with optimal transport methods themselves, but maybe you could go back to slide, I thought it was slide 35. I was just curious to ask a little bit more about, I'm not sure if it's 35 in the PDF or 35, sorry, it's 35 in the PDF. It might've been slide 19 in the numbering that you have at the bottom there. It was where you first described the optimal transport. Yeah, keep going. Yeah, that one. Go forward. Yeah, this one here. Yes, good. Thank you. So right. So you explained this. You motivated in terms of the mines and the factories. So I'm first of all, maybe you could just clarify for me. So what is the aligned? So first on the right hand side, number 5, those X1 to XP, those denote different number of TRs. Each one is a full image. This is the Frobenius norm between pairs of images.
No, sorry, yeah, it's unclear and it's maybe not consistent with the presentation. So yeah, here X1 and Y1 are different voxels.
Different voxels. So this is the whole time course of voxel 1.
Exactly, yeah.
Okay, all right. So what do you do if there are different numbers of voxels in 2 brains, or they always have the same number of voxels somehow?
So here it doesn't have to be a square matrix. It can be a non-square.
I see. You have 1 to P here, but it could be non-square. Okay. So then the aligned. So one question is it symmetric? Is the algorithm symmetric if I just place X and Y? Will I get the same answer?
Yes.
You will. Okay. And then R is this full matrix here. What is the aligned brain? I guess, how do I think about, where do I get the aligned brain from? You hand me back this R and it's a full matrix.
So
right
here, the R is basically, R is exactly the optimal transport plan. So here we solve, we minimize equation 6, and what we output, the R is actually a matching between voxels, which is optimal for this problem, but we can directly use this matching separately as an alignment transform, since it exactly solves the relative problem.
Right. So it maps X into Y space or Y into X space. But then do I just pick one and I'll work and I map them from X into Y space and then that's the aligned brain? Or is there some, I guess part of the reason for my confusion is that I'm thinking about this from the standpoint of the shared response model, where there's sort of one common frame that's like a latent map, which is generating the 2 data sets. So here is there a preferred coordinate system for the aligned brains, or it doesn't matter?
No, I get it. You know, the optimal transport in itself problem is not symmetric. So if you define your cost matrix from X, Y, here the transport plan will be minimized to transport X to Y, solving all those constraints. But if you do the reverse and you try to transport Y to X, then that's where I think the transform will be symmetric in some sense. But like the pure transform without any entropic smoothing should be invertible. However, yeah, with the entropic smoothing, maybe it's not completely.
I see. So in this case, it's not symmetric. You pick pick one brain as the reference brain and map the other one into the.
Yeah, it's a pairwise formulation. Yeah, completely. Okay,
great. And then can you explain the role of the constraint 1 over P to the P norm at the very bottom left there? I didn't understand why that. So in shared response model, we have an orthogonality constraint. Here we have, there's no, R is not orthogonal, right?
No, actually, no, it doesn't have to. I'm not completely sure if the family optimal transport optimizes on is not a subfamily of orthogonal matrices, but by design, the only constraint in the minimization here is what we call the marginal norm of the constraint, so that we displace each element of the histogram of the source histogram to the target histogram. And so here what we do is that we don't displace the signal, we displace the voxels. So actually what we want is exactly displace all voxels equally, because we want here voxels are splitted and pushed towards target voxels. And what we want is the mass of each voxels to be equally pushed, if it's clear. So that's why those marginal constraints are there, just to ensure that overall we displace all voxels equally. Because here we don't want to valorize especially some voxels. We consider that all of them are noisy in the same way, and so we want to take them just as a set completely equal and transport them to the target voxels. And so
that's what the 1 over P norm constraint does. It wasn't obvious to me why that choice of constraint.
Yeah, actually, so those are called the marginal of the coupling. So when we search for R It's actually so a coupling between two histograms. And what we want is in the end that this coupling exactly respects the histogram that we had that we put as those constraints.
I see. So we preserve probability mass or something.
Exactly. Yeah. Basically, you preserve the probability mass of your voxels, which must be equal.
Okay, great. So then other question is this a convex problem solving this? I mean, certainly the loss function looks convex, but I don't know about the shape of this constraint. Is it a convex optimization problem or non-convex?
Yes, it is. It's actually without any regularization, it can be solved just through a linear program, but it's a very strong computational cost. So Sinkhorn with entropic regularization is just a shortcut, a computational shortcut, but it's convex. Okay, great. And then I was going to ask about the entropy panel, the entropy regularizer. You didn't say too much about that unless I missed it, so I apologize if so. How did you set that, and how important is this is encouraging entropy, so you're wanting it to be a flatter matrix with higher, without, it's non-sparsity basically. Yeah, the obstruction spot solution without any regularization is completely sparse usually. So that is a very strong constraint in that we don't want we don't necessarily need for matching, because several voxels could hold similar information and we would want to match them in an end-to-end fashion. So here the regularization also helps a lot with the stability of the coupling and enable us to solve this equation in a way more efficient way. Then it also introduces an hyperparameter epsilon, which tunes the level of entropy we allow the coupling to have in the end. And so this epsilon, basically, we made some experiments in our first paper to show that having basically, if you have wrong metrics, very smooth couplings perform well. So having a very high epsilon perform well just because you have a very smooth matrix. However, what we've seen in practice on a different set of problems is that if you set epsilon to 0.1 and well normalized, so we can find simple heuristics that just provide couplings that are quite sparse, but perform well to transport information. So it must still be a bit smooth because just we don't hold in our data.
Okay, so how did you set epsilon for the comparisons you showed later? Did you set that by cross-validation or by some other method?
We just took an initial value of that we saw worked well. In general,
I see.
We normalize the kernel. So basically the cost matrix is normalized in some way. And so, so with this normalization scheme, 0.1 value of our epsilon works in very close cases.
Okay.
We could cross-validate it, but we didn't.
Okay. Yeah, so potentially you could do even better if you optimize that penalty.
Yeah, definitely. But we wouldn't want to have to reset it for every data set. I mean, we mostly want to release some methods that are usable by researchers presently. So. Okay.
Great. And then so one more question on the method itself. The shared response model has a very nice interpretation as a probabilistic model, in terms of factor analysis. You can think of it as a kind of factor model where each brane is generated as a linearly warped version of the original sort of template brane plus noise. And I was curious if there's is there any kind of probabilistic interpretation of this method?
Not that I am aware of, at least. No, we didn't try to interpret it, because you can always interpret those elements as a probabilistic flows of mass of voxels. So you could say that you would match activations in a probabilistic way between servers, but we didn't try to.
Okay. Problem for future work. Sometimes it's nice to think if there are ways to interpret it probabilistically, which allows you to import Bayesian methods, but I didn't know if that was something that you thought about yet. Great. So one more, let's see. Question about the compute time. You showed that it took 10 times longer, roughly, than I don't know what the reference, than maybe the shared response model. I was curious, first of all, to know what is the scaling like? So in other words, 10 times, that's for some particular data set size. You know, if I make larger regions, does it scale differently? In other words, do they both scale cubically or quadratically? How is the scaling with number of voxels? that you put in? Have you looked at that?
Yeah, so the basic scaling of optimal transport is in n squared.
N squared, okay.
So yeah, compared to other methods, obviously it's longer. Then usually we parcellate it. So now you have in k parcels. So now you have something which is in the order of n over k square times k, something like that. And you can find the right the best setup possible. Basically, it works for up to tens of thousands of voxels, probably 10,000 of voxels, at least thousands of voxels easily, because now there are better implementations of optimal transport which are quite scalable, but it will be still way slower than methods relying only on similar value decompositions and this way.
Okay, so squared scaling might be better than shared response model, which I think has cubic scaling because you have to take matrix inverses and log determinants. So it might be, I don't know, might be worth looking into whether this, the constant is larger, but that the scaling is better maybe than some of the other methods. I'm not sure if that's.
We relied a lot on the efficient implementation of the shared response model, which are not probabilistic.
I see.
Hugo Richard, you participated.
That's right. Yeah. Okay. Okay.
So.
Cool. So what is the hope for speeding up the? That was one other question I had. Are there approximate methods that could give fast? Are there fast optimal transport methods or approximate methods that would be, would reduce that compute time but give similar answers?
Yes, definitely. There are some schemes actually right now that here in optimal transport, for example, basically when you look at the cost matrix, you build a kernel from it, and some methods look at this kernel in a multi-dimensional way. So first, looking at the sub-resolution, transporting at the sub-resolution voxel, and then focusing on places where there are still a lot of potential to refine the matching. So these are methods that exist in optimal transport, and even some packages are well developed, but still they rely on GPUs usually, and they are quite advanced. So we didn't want to include them in our implementations that are still supposed to be for cognitive researchers that don't always want to use a GPU or something stuff like that.
Okay, great. Nice opportunity for future work on that. All right, then if you don't mind going to slide 34, I think it's the numbered slide. I had a question. Just you mentioned you had some new results that said after ROI alignment, and I wasn't sure what that meant. If you could you had one result where shared response model was doing slightly better than optimal transport, and then on the next one, this one here, you said improvement after ROI alignment, and I didn't know what's the difference between the previous comparison and this one here. Yes. I don't know what ROI.
The wording is a bit unclear. So here we didn't use any aggregation scheme. So in the previous one, we made some local, for example, regions of a few hundred voxels, and on each of these voxels we calculated different alignment and recompose them as a whole grain alignment, as I showed in the piecewise approach. And here we just focused on those regions, which are quite large, here a few thousand voxels at least, and performed alignment directly. So we just fit one shared response model for each region, instead of fitting a lot of them paving the cortex. And decoding is performed here into ROI instead of being performed whole grain as well. And so here, basically what makes shared response model really worse than optimal transport is one specific data set, which is called Neuromod, for which we took a large ROI of, I think, 8,000 voxels, something like that. And shared response model always yield us very bad results on this specific problem, no matter the number of components that we use. We went to up to 800 components to decompose 2,000 frames, so quite a lot, and still we had bad results. So yeah, this is the main difference here.
Okay, great. Yes, okay, so I had, let's see, I think 2 more questions. One, did you have any insight into why? I was surprised in a way that the piecewise methods work so much better than the searchlight. I might have thought the searchlight would be better because you're sort of allowed to smoothly move. Do you have any intuition or, I don't know, any explanation for why the searchlight methods were worse than the piecewise?
No, actually, yeah, there are two theoretical, classical, yeah. I mean, when you think of this, Searchlight would yield less border effects, but less regularity in the alignment. Basically, the smoothness of the alignment yielded by Searchlight depends a lot on the number of Searchlight that you use, because depending on the number of regions, you have more overlapping regions in each point. And so here we use the sparse version of Searchlight with still some overlapping, as it's advised by people who published it. So no, actually, I don't have so much insight. Obviously, it's way more efficient, and yeah, the gains, I guess, are partly because of, especially for optimal transport, which is a very regular method. If you then average several optimal transport men together, you lose this sparsity that is that helps, obviously. So this might be a good question also to investigate.
Okay, so if you did a less sparse version of Searchlight, it might be that would improve if it had more overlap. That's conceivable.
That's possible, yeah. But
okay, but that would be computationally more demanding.
It's in parameters, and it actually didn't help so much. So yeah, I don't have any.
Okay, great. And then my final question: your benchmark is showing still pairwise results. Is that correct? And I wondered if you'd had any chance to look at comparisons using multi-subject alignment, because I do feel like that would be one of the kind of things we'd really want to see is multiple subjects and aligning them all. My impression at the Princeton group is that there's been some tasks where they were only able to get results after aligning everyone to the same coordinates. And so I was curious, it would be great to have a benchmark that looked at multi-subject comparisons. Is that something you've thought about, or?
So the shared response model basically can be used as is. So here the results for the shared response model can actually be extrapolated directly to because we fitted all subjects in at the same time.
Okay.
Since it would make no sense to do it pairwise. So actually, the piecewise or shared response results can be extrapolated to those use cases. For pairwise methods, yeah, basically using a template would probably decrease by a few percent the gains. So leaving, not so much gains there, I guess. But then if you just want to do decoding on a large group of subjects, you would want to use an efficient and fast method. So probably the shared response model would be enough. You don't need a full resolution alignment. I guess that's what I would advise in this kind of setup. But then, yeah, we would definitely need to extend that with templates.
But you have a method for finding these templates shared across subjects, and I would expect you'd get even better methods if you used that sort of more powerful model than the pairwise one. Is that your expectation as well?
No, so we didn't try it because you also have a literature of ways of finding templates, and so we didn't want to compare both all methods, all aggregation, and all templates.
I see.
But here, what we saw is that using a template instead of one subject decreases a bit the accuracy. Probably because here you really suit all the data for this leopard subject in particular, which helps with the decoding task later down the road. So you would lose a bit using a template, I guess, in this specific context.
Okay. Great. So those are all my questions. Thank you very much. Very interesting work, and congratulations.
Thank you very much.
Thomas, your mic level is a little bit low. I don't know if you can speak louder or step closer to the mic or something. It's just a little bit hard to hear you.
Sorry. I'll step closer. Is someone muted or? I guess the next member of the jury can be Florent, since Michel the last time.
So Michel, I am allowed to ask a question now? Okay, I will assume that absence of response means okay. First, Thomas, I wanted to congratulate you on your work. And I don't know if you did your PhD with the canonical 3 years duration that we have in France, but it looks like a lot of work, so that was impressive. with all the work that you presented in the slides today. But at the end of your dissertations, you also put this section, which I loved, which was what didn't work. And that there were actually quite a lot of things there. And you also listed a number of things that were not directly relevant for your thesis, but which you did also during your PhD. So that's an impressive amount of work. Second, I also wanted to thank you for contributing to NILearn. I saw that you contributed to NILearn, and now my team is using NILearn quite a lot for fMRI data. So thanks a lot for that. And also thank you for your document that was quite clear. I really enjoyed reading the dissertation. I learned a lot. I was basically completely ignorant about the topic, so I really, really learned a lot. So thank you quite a lot for that as well. If I can make perhaps one suggestion about how to slightly improve the writing. Often you dive quite fast into formalism, and sometimes it can help to first give some intuition and explain verbally what you're going to do with the math, and then explain the math. At least for people like me, who are I'm a biologist by training, so I'm not very used to formalism. It helps me a lot when I'm first provided with the intuitions, the ideas. It helped me quite a lot to then follow the math and the problem when it is formally presented. But that's just a minor suggestion. The document was already quite pleasant to read. So now about questions. So I have one question, which is perhaps a bit a deep question. I was wondering this alignment methods. It looks like you make, I mean, not you personally, but assumptions are made about the type of neural code that is behind. And I imagine that there are some types of neural codes for which you can expect some advantage of using functional alignment, but also some other type of code, the way it is organized spatially and the way it can differ across subjects, which will make functional alignment hopeless with the kind of method that you've presented. And to clarify, so this applies to functional alignment, but this is even worse with the classic anatomical alignment. So I hope you get the question. My question would be, could you make more explicit what are these assumptions about the organization of the neural code that would make the neural code suitable to get some interesting result with alignment?
So I'm not completely sure. I'm sure what you put behind the neural code, but I guess the main assumptions of alignment, at least as a voxel matching technique, which it is basically technically, that's for a voxel. So still a large group of neurons, you could define quite well their functional characterization, in which tasks they take part as a group or as an aggregate of different subgroups that take part in different functions. And then, but of course, that this characterization can be robust in time. So if you repeat your experiments, you hope those voxels would be characterized in the same way. So yeah, basically, it's mostly an idea that voxels functions are, whether overlapping or not, we don't really care, since our activation profile can span a different range of functions, and multifunctional regions could still be well characterized. But we would still hope that voxels are, that their information is well captured by just this activity profile. I'm not sure it's a very precise answer, but I think it is the only assumption. It says alignment.
Okay, so perhaps let me take a concrete example. So imagine that you have a case in which you're doing some encoding analysis. So you assume that at the level of one voxel, you can model the activity with a linear combination of features, which is usually a quite nonlinear function of the stimuli that the subject is provided with. And if you have this, and the linear combination of features is quite different from one voxel to the next, and also from one subject to the next, in this specific case, I was having a hard time understanding how functional alignment could really help to align the subject. Those linear combination of features are quite different from different voxels and across subjects, but perhaps I'm wrong. So could you elaborate on this concrete example?
So here, if I understand, the activation profile would vary differently. Parts of it would be varying differently across subjects because of different combinations of functional networks in the same voxel across subjects.
Yeah, across voxel of a subject and also therefore across subjects too.
Yeah, so here it's mostly a question of noisy features. Basically, yeah, here we can match well voxels just as much as they are well characterized by those features that must be in correspondence across subjects, and each feature is given the same amount of importance in all methods I presented until now. So each images will have the same weight. So if we have two sets of features that have really different behaviors for different subjects and are not in correspondence at all, then I guess half of the features will be wrong and the overall alignment will be really bad. So yeah, we suppose still that those characterizations are, or dimensions of characterizations are stable across subjects. Meaning that, yeah, the effects we observe can be related not as a combination of underlying effects. There must be a specific to each task exactly.
Okay, thank you. And another aspect of this question has some practical implications, which is, so you need some data to train your, or to compute the alignment. And then you have some other data that you're really interested in. And so, yeah, I was wondering, of course, these are not completely independent. So perhaps there are some type of data that are better for what you want to do in the end. So let's take, again, a concrete example. Let's say that the task you're interested in the end is an n-back task. You have some example of that in your data sets. So what is the best type of data to use as alignment? Is a natural movie a good type of data to compute the alignment? Or are there other types of data for the training the alignment that would make it more likely to yield some benefit for the n-back task?
Yeah, so this is a very complex question because yeah, basically, if I get it well, you're wondering about how the data that you use to learn alignment will impact the alignment that you learn, and how it will affect every region of the alignment. So here, this is an ongoing debate because several people advise to use movie watching as data as characterizations, as a good overall characterization of the cortex, even though it's mostly probing sensory areas usually. So what we've seen, we've made some comparisons about this. It can still be worth showing it now. Because we replicated, as we have a few data sets that hold a lot of data, we were able to compare some of those. So here what you see are the same kind of decoding task, but applied very locally on 300 regions, and the decoding is just performed each time on the regions. So here it's completely independent problems solved in each dot, and how much gains we have very locally. This is done to have a sense of the local impact of data on alignment. And on the left column, you have one movie watching data set that was presented to several different IBC subjects and that we use as alignment data. And on the right, you have another combination of many contrasts derived from several task-based protocols and the same IBC data. And each row is different decoding task. So decoding tasks have different ascriptions, as we talked about in earlier questions. They characterize alignment in different regions of the brain. And now to the question of how do alignment stimuli compare, what we can see is that roughly, if we take a given task, for example, sounds in the auditory, which is about auditory categories, we can see that the alignment gains are located in roughly the same areas, whether we learn our alignment on radars or on more contrast with diverse components. If we took some other harder decoding tasks, not probing the auditory system, for which obviously movie watching data hold a lot of signal. So here we took another task trying to disentangle the 24 contrasts of the HCP protocol. We can see that the relationship between what is learned with radars dataset and on several contrasts is very different. It is very harder, is really harder to assess. Now it's not exactly the same regions in which alignment perform well for this task, meaning that when you just use some auditory or visual decoding task, obviously movie watching data will be fine alignment data because they hold a lot of this kind of signal. But if you had working memory, it would still work at least for the visual categorization part. But for the memory, it would be less well aligned. And if you took some other more viable systems, such as cognitive control or other things like that, then it's very hard to say which type of alignment data is take. Probably very related alignment, task-based alignment data. Like
okay, thank you. Thank you. I had another question, which was that's more a remark actually. So at some point in your dissertation, you mentioned this issue of how should I compare the different techniques and how good a given technique is. And you say that one difficulty is that we don't know the ground truth. You say that one possibility could be to take the average of many subjects, but with the caveat that this is you will detect mostly big blobs and not very fine-grained results. And the solution that you have come up with, which was cross-subject decoding, seems to be very clever to that respect. I wanted to ask you if you could also look at things which we know are organized at a very fine scale. So if I take an example, the phase patches in the ventral visual pathways. So with higher resolution and also electrophysiological work from monkeys and also epileptic patients, we know that there are multiple phase patches along the ventral visual stream. And for quite some time, we were not able to detect them with MRI because we were just averaging many things. And instead of different patches, we were just seeing a big patch. So I was wondering whether another way to validate the alignment methods could also be this, for instance, could be that after aligning, now you clearly see different patches instead of seeing one big patch. And we know that this would match what we know from electrophysiology, for instance. So what do you think of this idea of using as type of data to test your methods, data in which you know that there is a very precise fine-grained organization of the information?
Yes, definitely. Yeah. This is a very interesting. It's a very interesting idea of validation. Actually, this is a bit what was done in the first times of hyperalignment, because it's very tied to this idea of alignment, to be able to really find precise matching across subjects for very specific cartographies. So they did it a lot with retinotopic data, trying to show that they managed to align well retinotopic maps across subjects. But fine-grained cartographies are definitely a very good task, since it would also help us understand in this precise context whether our alignment methods would aggregate all those patches together or still be able to differentiate just through functional characterizations those patches one from another and predict a good template of that. So in terms of functional differentiation, it's very interesting. Then there remains the spatial location problem. It's still very hard to give a good visualization of those at some spatial locations that make sense because we would lose a bit the structure function coupling process.
Okay. And so I had another question about the issue of circularity. So if I understood correctly, everything that you've shown, the data that you use for the alignment and further testing, so let's say the decoding, these were distinct sets, distinct parts of your data, right?
Yeah, completely. Entirely. Always different alignment data from decoding or other evaluation data and completely independent training and testing sets, also different subjects.
Okay, so you don't have circularity in that sense. But there is another aspect of circularity or of non-independence, which is that, well, you still hope that the data that you have in the to train the alignment and the data that you will analyze in the end, well, you still hope that they are related to some extent. So, for instance, you will not use just some visual data for the alignment and then to test in a purely auditory task. It would be a bit meaningless. So, yeah, this something that I was a bit struggling with. You don't want to have non-independence and circularity in the sense of your data sets, but you still want to have data sets that are related at the functional level in terms of the cognitive processes. And yeah, perhaps that's not easy to get in any type of data set. So you analyze large data sets, the IBC and other data sets like this. But my question was, do you think that this approach can be used when you have basically fewer, less data typically, and you cannot very clearly make splits in your data between something that you can use for training, something that you can use for testing?
Yeah, it's very interesting. I never thought of it like that. The circularity of, obviously, yeah, by design, we chose some functional data for alignment and for decoding that had some, that probed some common networks, because otherwise it would be hopeless. And yeah, it's true that by design, we forced alignment to be good if they could. So then the algorithm still works, but yes, there is a kind of circularity. On top of, so to answer your question, so yeah, there is no clear consensus. Yeah, what we do is methodological evaluation of functional alignment methods. So here we obviously want to have as clean as possible evaluations with complete independence of our testing metrics and from our training process, because otherwise it wouldn't make sense to try to compare methods. Then if you just want to apply alignment to your data to lower the level of variability, you can always make it and go on with decoding, for example, if that's what you want to do. It would not impair your decoding process if you manage to, yeah, if you want to decode subjects for decoding, it could impair your results actually. But if you want to do inference, it would be possible to do it still in this aligned space. So yeah, the clear answer is obviously if you can, it's better to not have the same set of data. And if you need some independent validation schemes for your methods to be to have some statistical power, you still shouldn't. But for some methods, it's possible to apply alignment on the same sets that you will then use in downstream tasks, and that wouldn't harm. Obviously here, yeah, that was not our purpose at all, because we just wanted to do a comparison of methods in the previous data.
Okay, thank you. And my last question is, so I would definitely never be a developer of this technique, but perhaps one day a user. So it would be very useful if you could try to summarize what are the guidelines, what should we do? For instance, is it better to do those analyses on the surface or in the volume? Is it better to use unsmooth data or to smooth a little bit? Is there an ideal voxel size for it to work better? Is there a minimum SNR that you need data? Is there a minimum amount of data that you need to have something that makes sense in the end? Yeah, and could you now on the fly make such recommendations?
If I recall them correctly, yes. So first, it would be great to have some users for those methods because it's a lot why we did all this work. And so what we would recommend, so for surface versus volume, it's no debate. There is no clear proof that surface is better, but it's supposed to be from the literature. For smoothing, what we observed is that smoothing doesn't harm and usually makes results more stable. So we would advise a small quantity of smoothing. Also about what were the other ones?
Yeah, amount of data. Do you really need a lot of data to train the alignments?
Actually, it's not much the quantity, the number of time frames, but the overall quantity of signal. So we did it with 50 contrast from IBC, obviously derived from a lot more time frames, and it would still work quite well. And for movie watching data, we used from a few hundreds time frames, just 600 or 800 time frames. It was enough to derive good alignments usually.
Okay, and voxel size, what is the minimum voxel size that has been used successfully in previous studies?
So this is, we didn't make clear experiments on that, but we mostly proceeded with 3 millimeter resolution because we had a lot of experiments to make and to make everything comparable. However, it should not make any difference to work on, for example, 2 millimeter isometric voxels. Higher resolution than that, it's really an open question.
Okay, thank you very much, Thomas.
Thank you very much.
Thank you, Florent. So now, before giving the last word to Bertrand as a PhD advisor, I will ask myself some questions, although I'm not an expert in the in neuroscience, so some questions will be rather naive. I was wondering whether you tried the optimal transport between two resting states of the same person. So you see, that would give an idea of what is the variability of the patterns.
So the problem here...
Thomas, approche-toi du truc parce que je n'entends pas ce que tu dis.
Sorry, yeah, I was mostly trying to think about this suggestion. I'm not sure I understood it completely.
Okay, so you have activities, right? Yeah. And now if we know that this is the same brain, that is the same person, okay? And the activity is, for instance, resting state, but could be something else. I was wondering whether you could assess what would be the optimal transport between, I don't know, say Joe in resting state the Monday and Joe in resting state the Tuesday.
So we could do it from it's possible to do. Then I'm not sure if it would make sense because resting state is based on having no experimental protocol clearly defined, so no clear labeling of time frames of what is happening in the brain of Joe at each time point. And so here it would, where we really need for functional alignment usually to have synchronized time frames or at least matched features. So we need to know what is happening at each time, at each image, so that we are sure that those features are well matched and but we're not comparing features that are not the same. Is that clear?
No, I agree. But if you have something, right, if nothing is supposed to happen during the resting state, so you have something which is a sequence, and okay, and you have obviously something different before and something different after. And I was wondering whether this could be used to say, to give a baseline of what we can expect as the best thing, the best result.
Maybe, yeah, if we, resting state, actually, many things happen during resting state because there are a lot of functional systems that are actually activating. And so it's hard to know how we should match it. But if we take over test-based protocols, so classical setup, but just the same data, the same subject with different set of data replicated twice, yeah, that would clearly give us a highest bound on how much accuracy gains, for example, we can, and what's the best alignment we could possibly hope for.
Yeah.
Because
and
yeah,
yes, exactly. And
yeah, is that even this will be strongly limited by some other type of variability that exists. Is the intra-individual variability, or what is also called the test-retest reliability. So if the same subject does twice the same thing, it will be exactly the same data output. And so still, it won't be perfectly aligned from there. And the noise that we have will decrease the alignment benefits.
No, you're right. There are factors of variability all over the place. But the question is that if you're comparing a given brain with itself, right, then typically okay, so the question was, my guess is that this gives you an optimistic idea of what you can expect. And this leads to my second question, which is, so perhaps there is something I didn't understand well, which is the fact that you try to align every brain with a single template, right?
Yeah, depending on the experiment, but yes.
Yeah. And I was wondering whether it would be doable, and if you tried, to try to align, say, people by pair, because, and I think that this is a question that we have a debate with Bertrand for a few years, and the question is whether there is, there is this idea of what was the name? The atlas, right? The fact that you have a given, say, structure, and everyone is kind of a variation, a probabilistic variation of this single template. And I think that typically the optimal transport might be one way to investigate whether it's better to try to have one, say, single template and try to align everyone with the single template, or if you can, so the question is it doable? If you can align, I don't know, say typically Bob and Alice, right? And because if you can do this, and if you have a score, then typically you could have clusters on the brains.
Yes. So yeah, there are a lot of things in this question. Yeah, maybe the fundamental need for common representation space is just practical. In fact, when you want to do a group study, you would want all subjects after alignment to be comparable to perform your group study. And in which space do you want to perform that? So if you just make pairwise alignment, at some point, either you take one subject space as the reference space, either you don't have a common space and a block. So this is a first question that's motivated also by the idea of including it in an analysis pipeline. Then, yes, can we really match pairwise alignment precision with any possible atlas or template? it's hard to say. Optimal transport is in fact a good way to measure distance because those transport plans can actually be interpreted as a distance when they are multiplied by the cost matrix, the Wasserstein distance. And so if we know the distance between a set of subjects, we can then try to take their barycenter. However, here we don't have exact optimal transport plan between histograms of signal. What we have is histograms between the voxels. So we can use them, but they are not really characteristics of the distribution of signals of people. And so actually we can't make barycenters of them. For example, I developed that a little bit in my thesis. So the idea of having a Wasserstein barycenter of brains was the one that got this PhD started, I think, actually. But we didn't manage to do it quite in that way because brain signals are not histograms. And this is tough. There are tough limitations to overcome. So yeah, those alignments enable us to have some relationships between pairs of subjects. We could measure the norm at least of these alignments to have a sense of subjects that are alike or not in large cohorts that would enable us to cluster, and it would already be doable with what we did. But then we would still need a kind of common space when we want to perform group studies.
Yes, but typically when you validate the alignment by being able to achieve prediction goals, you could, okay, or perhaps you could not, but tell me. I think that you could consider the alignment with different brains and use the ensemble of those alignments to help you achieve the prediction goal. You see, you see how, and perhaps you could, okay, this the ensemble might be a way to have this, right? You don't need, okay, perhaps I don't think that you need a histogram at this point. You don't need the barycenter. You need to keep all the brains and to aggregate, and to some extent, what each brain might be saying on the behavior of the brain on the test.
Yeah, actually, that would be another way to. So here, what we tested is a smaller version of this idea, I guess, because we fixed a left-out subject and we brought everyone to his space. So we test a subset of this idea. What you're proposing, if I get it correctly, is to try to align each subject pairwise to every other subject in the training set, and so have n square images after alignment, set of images after alignment, concatenate all of that, and train, for example, if we are doing decoding, and train a decoder on these images. So now the question, yeah, we didn't try this. It's an interesting idea. The question is, do we have more examples showing more variability, and this will help the decoder, or as we have so many images that don't really belong in the same signal space, it will completely lose the decoder. We won't be able to train well-performing model. This is actually, I have even no bet on what will happen in this case.
Yes, of course. This needs to be experimented. I have a last question, which is the fact that you were using the Wasserstein distance between the brains. And I was wondering whether you consider the Gromov-Wasserstein distance, that is the fact that you are trying to impose the fact that the transport from one brain to another is a kind of rigid, right? You can't have, say, the transport which maps every voxel in the random order.
It's a very interesting suggestion. And actually, yeah, I didn't really consider it myself because we were still trying to roll out a method that would perform well computationally. And at the time when we did that, Gromov-Wasserstein implementations were really just starting. But yeah, there is someone else, which is actually in this right Visio conference, that is actually working on that in our lab right now.
Okay, very well. So I'm keen to see the more about this. So I guess that now I will perhaps ask if a member of the jury has another question, burning question, and wants to add something, just to grill a little bit Thomas. Or if not, then I give the floor to Bertrand, who is the PhD advisor of Thomas. Allô, Bertrand, tu m'entends?
We're in the same room, so I wanted to avoid any loop with the sound. Well, thank you, Thomas, for the great presentation, in my view. And I really liked Florence comment that the amount of negative results is impressive, and maybe it's a hallmark of the quality of your work. And then yeah, you did pretty good work, I would say. And indeed, I think you worked on a difficult field because the expectations from the community are somewhat distorted with respect to the hyperalignment method. I think that many people take this approach as something obvious that should be done on the data, but that actually nobody uses, or with some exceptions, of course, but it's still, I would say, quite confidential in terms of use. So there is certainly here a gap between what is expected from these techniques and the reality of what is the community has been doing with it. And of course, it's always hard to improve upon the state of the art when the situation is so muddy. And second point is that validation, you did some validation work and you dared to do it, I would say. And this requires a huge amount of work. Just one thing that was not really discussed here, but I think it has to be realized, is that you tried decoding many publicly available data sets, and it just failed on the majority of these data sets. So you spend all your time sometimes reanalyzing the data set to get the image to be decoded, etc. And at the end, you realize that the decoding was at chance. And okay, that's it. That's the situation of the community now. If you take publicly available data, much of it is actually not does not support better than chance decoding. And so you wanted to use only methods on which decoding was better than chance, otherwise the conclusion could be spurious. So in this situation, I think that the effort that you did, which was to provide good implementations, is already a very important step, and I think the point has been made by some members of the committee. Maybe on a more personal note, it has been a pleasure to work with you. And indeed, it lasted only 3 years. You did it in 36 months, according to a French regulation. You were really autonomous. You ran the project by yourself. We had some relatively frequent discussion, like weekly typically, but really you were autonomous in taking decisions and moving forward with the project. You had lots of critical thoughts on what we were doing, what others were doing, and you always tried to understand, open the discussion, and I think the discussion we had now illustrates that you are willing to both to acknowledge the limitation of what is done and go further and understand what could be the next possible direction. Another feature is that you've been very realistic in the way you were handling the work. You took care of implementations. You wanted to have something that was consistent, that you could essentially prove in everything you showed. And maybe even more importantly, you launched really the international collaboration with Elisabeth Dupré on this topic. So it's some ongoing work. Elisabeth has been associated with actually the image that is shown at the moment, is displayed at the moment on the Zoom, is some current work done with Elisabeth. And all this was done based on your initiative. And it's great that you, as a PhD student, you can take the initiative to have a broader collaboration and to build a true network of true collaborative network on this topic. As pointed also by Florent, you've been playing a great role in the development of NILEARN. Actually, you've been a member of the core team that has been meeting monthly for 1 year, but also taking part to all events, coding sprints. You took a lot of time to organize it. And it's really impressive that on top of your PhD work, you did this community work. I think you enjoyed it, but still, thank you for doing it. We need people like you. Better than that, or more than that, you've also been involved in the life of the team with the organization of the team meetings, and that has been great. I mean, it's awesome that also people like you can well devote some time to the common organization. Well, all this has been really great, and I would like to thank you now for all that. My only regret is that I wish you got more fun from doing it. I think at some point it became a bit dull to run all these validation experiments, and maybe that's why you are moving away now. But I think you've built excellent blocks, and there is some research in the team going on based on what you've done, and this is really nice. So thanks a lot for all that.
Thank you very much. Thanks.
So thank you, Bertrand. So I think that now all the jury will move to the private link that Bertrand sent us for the deliberation. If someone didn't have the link, perhaps say it now, and Bertrand will resend it to you. Okay.
I just pasted it in the chat.
Ah bon, ok. Mais attends une seconde.
May I ask you to leave for the committee discussion?
Tu veux le bon.
So I'll just leave
okay.
the account open.
Okay, so the Zoom will remain open for the final part of the ceremony, which will take just a few minutes after the committee discussion. But now, so we just leave. You can all leave the Zoom room and switch to the BlueJeans link that I sent you. Oui. Oui. Yep.
Good, excellent. So, Thomas? So I have the pleasure to tell you that the jury appreciated what you did, your presentation, and that you presented a very good selection of your research work in the domain of brain imaging and functional alignment. The jury liked the fact that you gave a comprehensible and pedagogic description of your results that was illustrating the difficulties and the benefits from achieving a principled inter-subject alignment. Your presentation was very clear, and you did an excellent job answering the jury's questions on a variety of different topics, ranging from technical questions about the methods you developed to questions about the benchmark comparisons that you presented, and open-ended theoretical questions about the future of research on brain alignment methods in fMRI analysis and more broadly in neurosciences. In your responses, you demonstrated once again your competence, your ability to be critical when evaluating your own results, and the capacity to identify future directions for the work. Overall, you showed that you mastered the topics that you presented in your PhD defense and oral presentation. And for all these reasons, the jury deems that you deserve the title of PhD in computer science from Université Paris-Saclay.
Thank you very much.
And now we can clap hands, kind of. Yeah, voilà.
Congratulations.
Yeah, congratulations, Thomas.
Thanks a lot.
Congratulations, great work.
Good.
Am I allowed to say just a few words very quickly? I'd like to thank you, members of the jury, for accepting to spend this time examining this work and reviewing it for the reviewers as well. Thanks a lot for reading it and by overrise that's ours. For other people that participated in this defense in physics, even though you didn't really know the members of the jury. And thanks to Bertrand a lot for all these years of supervisions, and he taught me great stuff. Yeah, thanks to everyone. Let's celebrate this. It's pity we can't celebrate this all together, but next time we pass in Paris. Yeah. Thanks a lot.
Okay, so congratulations again, Thomas, and good future. Yeah, all our wishes for you. Okay, goodbye.
Thank you very much. Have a great day.
Félicitations.
Oui.
À la prochaine.
Okay.
Bonne continuation.
Merci beaucoup.
Au revoir.
Merci à tous.